Tarda media hora más.
So, good morning. I know that you are quite tired, so I will try to do it easy. My main objective is to let you understand at least the problem that I want to show you, and then you can, if you are interested, you can find some more details in the paper that you have in the documentation. Okay. My name is Chiumenti. I'm Italian, lost in Spain. And Miguel Cervera is the co-author of this presentation, and we have different PhD students who contribute to the result and the idea that we are going to show you. The idea is to tell you what happens if you have some kind of strain localization during the simulation that you are carrying out. And this can happen either if you use plasticity models, as the one that you have been studying in this course, or if you are using some damage models. Okay. In both cases, you can reach the failure of the structure at different modes. Let's say mode 1 means crackings or sliding, which is more typical for metals. Okay. So I will go through some idea of what is failure, what is strain localization, and how to tackle this through finite elements. Okay. What's the main problem here? And the only thing that I would like you to understand. Plasticity models, particularly if you use J2 plasticity, give a solution which is mainly isochoric. Isochoric means that they preserve the volume. Why? Because all the deformation come from the deviatory part of the strains, and this means that the deformation in plasticity are because of the change of the shape and not the change of the volume. And if your solution is almost isochoric, like in plasticity, typically you have a locking of the solution. This means that if you use classical standard displacement-based elements, you can get locking. I will show you the examples. And pressure oscillation also. If you have some kind of strain localization, I will show you now, there is a second big problem that you should avoid, which is the mesh dependency. So part just break in the simulation according to the bias of the mesh and not to the actual direction of the cracks. So both isochoric problem and mesh dependencies are the two key points of this presentation. And I will give you a solution. There are different solutions for this. I will give you our proposal to solve this problem. Okay? So structural failure, as you can imagine, you can think about, can happen in different kind of engineering fields, in civil engineering, in aerospace, any kind, for different kind of material, as I told you, plasticity, damage, whatever. And this can be due to defects that you can find into your components, or because of an inadequate design, or because of the in-service loading, which we can reach the failure of the structure. Okay. The second important stuff is that you can get failure and strain localization, leading to failure at different scales. And I will show you later on that this induces a size effect phenomenon. So you can have failure at small scale, meaning displacement in the lab, up to large sliding. This is also mode 2 strain localization. And so completely different scales, from centimeter to kilometers. Okay? And as you will see later on, the same material behavior show a different structural behavior according to the scale. This is called size effect, and we'll show you later on. So this is a specimen used in a tensile test, and you can see that increasing the loading, you have a localization of the strains up to the failure of the part. Okay? This is not finite element. This is just a grid on a specimen under loading. Okay? Just to show that you effectively have a localization of the strains. And so the idea is which kind of finite element technology you need to tackle this kind of localization. Okay? So what is failure? Failure means that you reach the ultimate state of the material, or in this case of the structures. And typically when this happens and the structure is going to break, you have a release of energy, and this energy is the so-called fracture energy. Okay? This fracture energy is the energy dissipated for the opening of a unit surface area of your cracks. Okay? And this will be one of the ingredients of one of the data for the simulation. I will tackle here two couple and very distinct kind of strain localization leading to cracking. One is the so-called mode 1. This is just crack. Typically, we tackle this using damage models. Okay? The second one, more related to what you are doing here, is mode 2. This end up with slip lines. And typically, we solve the problem this kind through a plasticity model. So the idea is you have a plastic model, J2, and you want to get this kind of solution, and you want the solution to be accurate, meaning not depending on the mesh and not depending on the isochoric constraining of the model that you're using. Okay? So you have mode 1, mode 2, and I will show you two different solutions, finite element solution, to work with this or with this. So, first of all, when you are going to have a crack, you typically have a discontinuity in the displacement field. Okay? We call it strong discontinuity because you have a jump in the displacement. You are breaking, so you have a jump in the displacement, and because the strains, as you know, are the derivative of the displacement, if here you have a jump, here you end up with an infinite value. So you have an unbounded strain value. It's clear. So here you have a jump, and here you have an unbounded strains, because this is the derivative of this function. As you can understand, this is difficult to tackle by finite elements. Okay? So the second possibility is to say, okay, we can try to regularize this jump within a band, and the size of this band is B, okay, at continuum level. So in this case, the same jumps as before, it is mirrored, it is regularized through a band of this size. And this allows you to have a bounded strain field. Still discontinuous, but bounded. So you can work with it. Okay? Now you can say, okay, but which is the size of this band? You want it the smallest, because the actual solution is a jump. Well, in finite element, if you have a discretization, the smallest size of this band is one element through. So if you have a fine mesh, you have a fine band. Okay? As you will see, the solution is very nice, just using this. Okay? It's not necessary to reach the fully strong discontinuity. And I will show you the result. Okay? But the question is, our solution goes through this kind of approach, where we smear the jump into one finite element. Now, the problem is that if you use standard finite elements, you use this kind of discretization, you run a simulation increasing the loading, you end up with two big problems. One is the mesh dependency of the solution. So typically, material cracks, the solution that you get depends on the orientation of the mesh. So if the mesh is like this, you will break like this. And second, you still have a problem due to the isochoric response of the material. So the idea is what to do. Just to give you a small example, if you want to do this very easy example, easy test, this uniaxial tensile test, and you use a Cartesian mesh oriented this way, where you expect, using a Rankine model, for instance, to break here, you get perfect solution. But if instead of this mesh, you decide to use, the accuracy of the projector is not very well, but this is a mesh which is slanted like this, okay? So exactly the same boundary condition, exactly the same material, everything the same. I'm just changing the meshing, and this is the result that you obtain. So just changing the mesh, the solution is rubbish. Okay? So if you pretend to go through failure, strain localization using standard element, push the button in your PC, this is the solution that you obtain. Okay? So as you could see, when the mesh is fine, it's oriented according to the expected result. So if you know the path of the crack, you can align your mesh that way, and you can attain the right solution. The problem is that not always like that. So according to our understanding, the problem is not the continuum model that you're using, so the equation that you are using. So you don't need to modify the equation. The balance equation are the balance equation, finish. The problem is not the constructive model, because as you saw, when the mesh is well placed, the solution is perfect. The solution is the spatial discretization, so the finite element that you are using, that are not able to catch the solution. And I will show you both in mode 1 and mode 2 how to solve this problem. So which element you should use. Typically, in mode 1, meaning cracking, the problem is the low accuracy of the strain and stress field. So the stress field is not enough good to find the good orientation of the crack, and so the cracks go through the mesh. This is the main problem in mode 2. In mode 1. In mode 2, meaning sliding, plasticity, the problem is the isochoric behavior of the constitutive equation, which lead to locking. Okay? So our solution, and I will show you just a brief review of our solution, is to tackle this through displacement strains finite elements, and to tackle mode 2, we are using displacement pressure formulation. So in both cases are mixed elements, which use more degree of freedom at the nodes. So not only displacement as the classical finite element, but as something else. This is the classical solution used in incompressible flow dynamics that we import into solid mechanics. And this is another kind of formulation able to solve the cracking. Okay? The idea is similar, and the technicalities are quite similar. And you can find this in the papers. So the idea can be resumed just in this slide. If you use a solution where the unknown are just, at the nodes, are just displacement, the classical one that everybody used in the industry, the solution is typically not very good in accuracy for stresses and strains, and is not able to play with isochoric material. Forget about it. This means that if your solution is an elastoplastic solution, you just need to reach the elastic limit, okay, this works. But if you go behind the elastic limit and you want to reach a strain localization, these strain deformation are isochoric, forget about this element. The solution will lock, and I will demonstrate to you. Next, if you use a displacement pressure solution, which is the one that is typically used in CFD analysis, this is fine. It is fine because this is a technology used to tackle incompressibility. So it works, at least it works, to solve mode 2 analysis. For instance, it works with elastoplasticity. Very good results and very easy to implement. Finally, if you want to reach the highest level of accuracy doing cracking, mode 1, typically using damage model, concrete, stones, whatever, you need something else. And the something else is an enhancement through strains at the nodes. So at the nodes, you have displacement, but also strains. You could say, okay, but if I have everything, so if I have isochoric problem, cracking, whatever, it exists another formulation that is just published in the last year, and one of the papers from this year is the three-field formulation, which include displacement, pressure, and deviatoric stresses at the nodes. You can think this is very expensive and very complicated, but at the end, it's not like that. Okay? Any case, mixed finite element just it's something that is not new. The problem of mixed element is that if at the same nodes you have different field, so you are going to interpolate the displacement at the nodes and also, for instance, the pressure at the node, you cannot choose any kind of field. So if you want to use a linear field for the displacement and a linear field for the pressure, these two fields are incompatible, so lead to instabilities. So this is why in more recent year, it appears the subscale method just to prevent this kind of problems. And also the orthogonal subscale by Ramon Codina in 2000 also offer a solution to these things. So at the end of the day, for instance, if you want to use a displacement pressure solution, because it allows you to solve elastoplasticity problem, you should work with quadratic field in the displacements, quadratic element for the displacement, and linear element for the pressure. This is expensive and has some other problems, but should work. It works. But if you want to use a cheaper element where you use linear displacement and linear pressure, this is incompatible. And so you need to do something else. This something else is a stabilization technique, which is just details that I don't want to enter into that. But the question, you can modify, add one term to the solution, and you can get this. We were working on P1 in displacement pressure elements for incompressible elasticity, rubber materials, this kind of materials, for elastoplasticity, and then we moved to two-field problems where we are using displacement and strains. And we accommodate the stabilization using the same idea presented here in these first original papers. So now I will show you what happens if you want to play with mode 2 analysis, so you want to see something like this, and then what happens if you want to tackle mode 1. Okay? So very few equations. No, I don't want to enter in any complexity. This is the balance equation of the mechanical problem. The divergence of sigma plus the body force is equal to 0. Strong format. This is the weak form, so the integral form. Okay? Everything is fine. If you have a formulation which is based on displacement, typically you compute the stresses through the displacement. So the main variable are displacement. So from the displacement, you derive the displacement field, you get the strains, you multiply by the constitutive equation, constitutive tensor, and you get the stresses. So the stresses are a function of displacement. This is the classical one. Okay? Perfect. This means that you have a weak form for the balance equation, the one who's solving the problem in the domain, while the constitutive equation is solved at the Gauss point, where you catch the displacement, you transform into strains and then to stresses. Okay? Classical one. Now, let's assume that you can split the stresses into the volumetric part, the pressure, and the deviatoric part. You saw this the first day yesterday. Okay? So this means that you switch from this balance equation to this one, which use as variable the deviatoric stresses and the pressure. No difficulties. Next, the solution, which is very much adopted in the computational fluid dynamics and now for incompressibility in solid mechanics, use as a main variable, driven variable, the displacement and the pressure. So this is the balance equation in strong form. This is the balance equation in weak form. But now the pressure is a variable at the node of your mesh. So it's a main variable. Okay? The deviatoric stresses are computed through the as before, in strong form at the Gauss point, and typically it's 2G by the deviatoric strains. Okay? The news is that this equation is the deviatoric part of the constitutive law. It's just deviatoric stresses versus deviatoric strains. Now, the counterpart, the volumetric part, is the pressure is K, the bulk modulus, multiplied by the divergence of formation. Okay? If you write this way, allow you to say, okay, if K tends to be infinite, because Poisson is 0.5, for instance, okay, this disappears, and you end up with this equation. This is available for fully isochoric problem, CFD, but also for elastoplastic analysis. Okay? And so what we do, because we need two equations, you need two equations. Okay? So the first equation is the balance equation in split format. The second equation is this equation in weak form. So you multiply by a test function, which is Q, and you integrate over the domain. As for the previous one, exactly the same. So you have two equations in two unknowns, the displacement and the pressure. Is it clear? So at the Gauss point, you only compute the deviatory stresses to be integrated here, not the full stress tensor. Okay? Now, as I told you before, if you have displacement and pressure at the nodes and you want to choose field interpolation for this, you are not completely free to do anything you want. So there are some restrictions. I don't want to enter into the details, but this is due to the which give you some rules to choose this kind of field. Okay? But if you want to forget about these constraints, you can overcome this constraint using stabilization. I let the details in the papers. Okay? Forget. Now I just want to let you understand the idea. Next, this is also quite well known, but I go through it. If you are going to break a part, I have strain localization, you typically, as you know, you are opening a surface due to the cracking. So you typically, your input data is the fracture energy, and if you multiply this fracture energy by the area of the cracks, you have the full energy dissipated in the cracking. So the fracture energy is for unit of area is G. If you multiply it by the area, you get the energy dissipated into the cracking process. Okay? But this is interesting if your solution is a strong discontinuity solution, when you typically have a jump in the displacement and you typically generate the surface. But we are not doing this. Why? Because we are doing a smear approach. So we are localizing the strains into the element. It's only one element. So you typically have to dissipate the energy in this volume where you have the localization. Here you can compute the dissipation, the mechanical dissipation. Typically is sigma by epsilon. Okay? So this dissipation is within a volume. And this volume is made by the same area as before, and H, which is the size of your crack, the thickness of your crack. Okay? So on one side, you have the fracture energy. On the other side, you have the dissipation, which work for unit of volume. Is it clear? So the relationship between the fracture energy and the dissipation depend on age, on the size of the cracks that you are used to regularize the crack or the slit line. Okay. Now, what is the dissipation? The dissipation is the area below the stress-strain curve. But if the dissipation depends on H, because you want to maintain G as fracture energy, which is your input data, this means that if you have different H, you need different softening curve. This is called a softening regularization of the model. So this means that your constitutive models must be modified according to the value of H, so that when you dissipate through this element of size H, you end up with G. Okay, so this is something that the software automatically does, because the software knows which is the size of the element and adjust the softening curve accordingly. This is not a trick. This is just a method due to the smearing. Okay, everybody does. So it's not okay, but just to let you understand that you put the data and the software modifies the data internally to guarantee the dissipation. Is it clear? So now let's go to see what happened. This is just a benchmark. This is a quarter of a tensile test where you have a specimen with a small hole. We go to the tensile test, you want to break it, okay, using elastoplasticity. You can do at home, okay? You use ANSYS or Abacus, whatever you want, commercial software, you apply the load. There is example, just this rectangular domain with a small hole. You use standard elements, and this is the solution you get. Rubbish. Why? Because the solution is going through the bias of the mesh. So in this case, the mesh is unstructured mesh, but it always has some kind of structuring, typically 30 degrees, because the mesh generator typically tend to generate equilateral elements. So the solution is kind of rubbish stuff. The second plot is what you obtain using a UP formulation, a mixed formulation. As you can see, it is able to skip the bias of the mesh and to catch the solution. So what's going on? If you use standard element, you typically have a locking that is shown in the pressure contour field. And this pollulates the solution and destroys your solution. If you run with the UP formulation, you get the right solution. Something else. If you change the size of the mesh, obviously there is a small differences because of the accuracy of the mesh that you are using, but typically you don't have the double of the dissipation. Why? Because you are using the regularization. So here you are changing the mesh from 1 to 0.25, and you get almost the same solution. Well, this is an old result, and now we are doing something better because this mesh is quite coarse. Okay, but the question is, if you reduce 4 times the size of the element, the dissipation is almost the same. So this is another example where we are changing the solution to a Drucker-Prager model, so not exactly J2 plasticity, and now you have different angles of the solution. Okay, and you can see how the mixed formulation is able to give you the exact solution according to the friction angle you have. Okay? Once again, if you try to do this with standard element, you don't get this kind of solution. Impossible. Okay? This is another very classical example that we use to check our finite element technology, and this is the Prandtl test. This is what's happening if you use standard elements. You can try. Also, another very easy example. You just push a block, rigid block, and you can see that the pressure is completely locked. And due to the locking of the pressure, you have a solution in terms of strain localization, which is also rubbish, and typically it is mesh dependent. If you use a mixed formulation, this is what you are expecting to get. Okay? These are very easy examples that you can try at home very easily. So 2D example, very different friction angle, very good solution. Okay. The expected solution, the numerical solution. Another of the disadvantage of using standard finite element is that the locking not only demonstrate on the mesh direction of the solution, the mesh dependency, but the locking also demonstrate on the peak value of the loads. So the failure of the structure should be here, and the standard element tell you that the failure is here. Completely wrong, but the error is almost 50%. Another stuff that I think you know, and if you don't know, it's better to know, is that if you perform exactly the same experiment, if you want a tension test, changing the size of the specimen, only the size, the same mesh, the same constitutive model, the same everything, you just resize the specimen from small one to big one, so from millimeter to meters, exactly with the same constitutive equation, typical elastoplasticity, okay? So this is a small specimen, this is a bigger one, this is a huge one, okay? The solution in terms of load displacement, in this case we normalize to be able to show in the same graph, is that if the specimen is very small, you obtain what you expect, and you expect an elastoplastic result. But increasing the size of the specimen, you get a structural response which show some kind of softening. So the material looks more brittle. And when the part, the component, the structure is very large, you can think of a bridge or ship like this, which is a real example. The result is that you get a very brittle result. So you apply the load and crack. So using the same mesh, the same constitutive model, the same fracture energy, because of the size, the material behaves from perfect plasticity to linear elastic fracture mechanics. Really brittle. This ship just breaking the harbor. Another concept is that not only the material, the structural behavior shown is more brittle, but also the nominal stress look smaller, lower. Okay. So if you expect a nominal stress to be here as your constitutive model, the structure will break with value which is decreasing according to the size of the specimen. This law is a very well-known law, which says that for small length scales, your nominal stress is what you expect, but increasing the size very much, 10,000 times, the nominal stress reduces accordingly. And so you go from a solution of the typical elastoplastic analysis to the solution of linear elastic fracture mechanics, where you have this kind of 2-1 slope of the solution. We did exactly the same. We repeat the same numerically, just using a tensile test you can find in the paper. just changing the size of the displacement, and you can get effectively this kind of solution. These dots are the trial that we did. And you can see that without changing nothing apart from the size of the displacement, you get a solution which is completely different. So show much more brittle of the expected. This is called size effects. Okay? So particularly if you work in an industry building big structure, take care, because the failure is completely different from what is expected. Well, there are a number of references. You can look in my webpage, you can find everything you can download. Now, I want to tackle, just to conclude my talk, what happened in mode 1. Well, what we were looking at was mode 2, typically, but we have also a solution for mode 1, meaning for cracking. And I want to let you understand the main problem. Okay? Then there are different solutions to solve this. Okay? Our solution is mixed elements, but you will see tomorrow, no, today, in the conference, that there are different kinds of solutions. Okay? Our solution, first of all, I want to introduce you the problem, then everybody is free to find the solution. What happened? If you have a component, in my case, it is just placement like this with initiation of a crack. Okay, can be anything. Okay, can be just the corner of this place where you have a stress concentration. Okay, the question is lesson 1, finite elements. Okay, lesson 1. How the solution converges to the right solution according to the size of the elements. So you have a component, you have to make a mesh, to generate a mesh. This mesh can be coarse, can be fine, and you know that if you refine the mesh, you converge to the actual solution that you are expecting. Okay? How fast is this convergence? So if you reduce the size of the element is half, how accurate is the new solution? So lesson 1, finite element. At global level, global means the full structure. The displacement are converging with the square of the edge. We are talking about linear elements. Huh? The strains converge order H1, so H, linearly. Why? Because these come from the derivative of the displacement, so one order less. The stresses converge as the strains, because are just the strain multiplied by C, by the constitutive tensor. So, at the end of the day, at global level, the ship, if you make a finer mesh, the convergence go from square to linear convergence for the strain and the stresses. And you could see, okay, it works. But if you now go to a place, a critical place, like the tip of the crack, or a corner in any of your components, where you have a concentration of the stress, and you want to know which is the rate of convergence in that place, so this is a local estimate of the error, typically you lose one order of accuracy. And so the displacement converges order H at the tip of the crack. But the strains are one order less. So you don't have any guarantee of convergence of the stress at the tip of the crack. This is why, if you use linear finite elements and you want to solve this problem, the solution is not guaranteed. So typically, you have a solution which is wrong. And typically, it breaks along of the bias of the mesh. Now, if you use a solution, a finite element technology, where you have both the strains and the displacement at the nodes, the displacement will converge globally, H squared, but also the strains, because you have an interpolation at the nodes. And also the stresses. So square, square, square. And locally, it's true that you still lose one order, but you still have one order of accuracy. So it is lower, but you get the convergence. So if you refine the mesh at the tip of the crack, you ensure that the software, the solution, is able to find the right path of the crack. You don't need any tracking technique to find the path. You just plug in, and the problem is just less than one finite element. You don't have any guarantee of the convergence of the stresses using standard elements. So I don't want you to exit from here with complex stuff in your mind, but just to understand, first, isochoric problems are dangerous. Second, where you have a stress concentration, you need to do something. If you don't do that, goodbye. So, what happens if you use standard elements? If you use standard elements, you typically, I draw the principal stresses. Okay? You expect to break orthogonal to the direction of the principal stresses. Okay? And at the end of the day, the material breaks like this. Why? If you use a mixed formulation, you typically have this kind of solution. This is the easiest example you can also try to do at home. 2D super stupid example. So, which is the solution for this kind of problems? The balance equation, always the same. Weak form, classical one. But the stresses are computed from the strains, and now the strains are computed at each one of the nodes of your mesh. It is one of the driven variable. So you are not coming from this displacement, are main variable. Okay? Constitutive equation. This is the classical constitutive equation. You can make more or less complex. You can change this with a second version of plasticity, damage, and you can if you want. Okay. The question is, you have two unknowns, the displacement and the strains. You need two equations. This is the balance equation. This is the constitutive equation in weak form. So you have two equations, okay, and two unknowns. Okay. Once again, you cannot choose the field as you want. There is the LBB constraint. You want to overcome stabilization. Papers. Okay. Technical details. Okay. Now, you could say, but if I have the strains at the nodes, the simulation is super expensive. It's clear because you have a lot of unknowns to each one of the nodes. Solution. The classical displacement-based formulation and the mixed formulation, both for the UP or for the U epsilon, are compatible with the standard one. So here you can use U-based formulation, and according to an error estimator telling you where is the stress concentration, the strain localization, you can activate the degree of freedom of the epsilon. So you use the Ferrari element here and the 500 here. Okay? Fully compatible. So I show you some example. This is a 4-point bending test, very classical example. Different meshes. Well, the resolution is not very good. You can look in the paper. Use the projector. It's low quality. But you can see that different meshes give you exactly the same solution. And if you integrate this area, this corresponds to the energy dissipated in these two cracks. It's exactly the fracture energy by the length of the crack. We check it. Another detail. If you make a zoom of what's going on here, you look at the notch, and you make a cut, and you plot the displacement and the strains. And you can see that even if we didn't use strong discontinuity, we just smear the crack in one element, you get a jump. Obviously, you cannot see it, but the size of this is one element. Okay? But to any effect of engineering computation, you get the jump was expected. And you get the strains. You can compute the strains are bounded. Okay? So, look nice. Now you can do it with more complex geometry. This is a pull-out test for concrete. So you are pulling from here, and you are breaking the specimen. If you use standard element, completely mesh-dependent solution, if you use mixed finite element, you get the same solution for any kind of mesh. Okay? Obviously, the finer is the mesh, the better. Okay, but good solution for, let's say, complex problem using tetrahedral elements and element. This is Rankine model. Okay, this is a torsion test. This is a predefined cut in the bar. You do the torsion, and this is the experimental result. This is the numerical results. No tracking, no trick, just mixed formulation. Just switching the finite element technology, nothing else. The costume model is the same. The balance equation are the same. Nothing changed. Just the finite element technology. So my final advice here for you is, if you want to do something complex, little bit far away from linear elasticity, take care which element technology you are using. I'm sure that in any of the software you are using, there are the possibility to choose. Well, select the good one. This is a piece of chalk. You can do the example at home also. This is our photo. Okay? Under torsion. This is the solution, the numerical solution using different, also the resolution is not good, but using different constitutive equations. From Rankine to Beltrami, Drucker, different kinds. But on this side, this is the numerical solution, this is the experimental solution. So once selected the right constitutive equation, you get exactly the same solution. This is numerical, experimental, numerical, experimental. This is our photo in the classroom. Nothing else than selecting the constitutive equation you want to use and the finite element technology able to deal with it. References, huge number. We were working in the last almost 10 years in this framework, and we had different PhD students. This is not fully updated, but if you look in my webpage or in the webpage of Professor Cervera, you can find the most new references. Okay. So, final. But I said, take care on the finite element. If you want to play only with isochoric problem in elastoplasticity, the solution is typically a mixed UP formulation. It works very nicely and it's cheap. If you want to play with cracking, there are different alternatives in the state of the art. You can find in the conference. Our solution is this one. I told you why. And also, I show you that it works. Okay? You cannot choose any field you want, any kind of interface you want. You need stabilization. These are technical details that you can find in the papers. And the result of this is that your solution is not mesh dependent or does not suffer of any locking due to the pressure constraints. You don't need any cracking technique, which is one of the solutions proposed years ago. And at the moment, we are working on this kind of solution, which includes the pressure and also the strength. This is the finite element, able to do anything, from plasticity to damage. Well, obviously, it is a more complex formulation. You can find in a couple of papers that we just published, one of them last year. It worked very well. Obviously, it's a more complex formulation, but the idea is exactly the same. This one is for isochoric solution. This one is for strain localization in mode 1. Okay. So thank you very much and good luck. We have a few minutes for questions. In any case, I will be around in the conference these days, so you can ask me any question.
Okay. I have one question. I'm just curious, so would it be straightforward to implement these techniques in the particle finite element method to obtain independent independent results?
In the particle, not straightforward, and I don't know why you want to do that solution in the particle one, because the particle methods use completely different kind of balance equation and quantitative equation. Because in fact you are using rigid movement of the particle, and then the quantitative equation is through spring or whatever between the particles.
Right. So we learned about the particle finite element yesterday, and there's also the meshing there. So could this be applied to sort of the elements in PFM?
Yes. The element technology can be imported into any parallel code, parallel information, and PFM uses a parallel information. So
This is not particle in terms of them, it is a particle in terms of PFM.
Yes,
And
exactly.
PFM is a sort of fan in the Lagrangian framework, so fine, including a movement of the mesh which is following the flow and whatever. So in this sense, if you are talking about PFM, the answer is yes. This is exactly the same framework, but you are just adding is a remeshing technology able to move the frame, okay? Because you want to solve complex problem with free surface and whatever. So in this sense, yes, I was understanding that. So discrete element method is not the case at all. The other one, yes.
I would have one question about size effect. So you said that the nominal strength will be lower for larger specimen size.
Yes.
But is it due to the effect of the stress concentration, or if I would have like a homogeneous bar and just increase the size, so no notches or anything, I find it a bit difficult to imagine that the peak load, I mean the peak strength would be different, because we always input the strength as a kind of parameter. In the
Locally, your strength from the computer model is the same.
Yeah.
But globally, at the size of the part, what you see as the loading displacement is the solution which depends on the size.
Okay, I can imagine that the softening part would be different because of the energy release, because we have larger, let's say, volume, and the crack surface is like scaled quadratically, and this is scaled cubically. So this is the difference. But I just wonder about the peak load. I mean, about the nominal strength. If there are no notches, if there is no stress concentration, I mean, I would just assume that homogeneously stress is increasing until we reach the strength. Then
In this case, you don't have any localization, which is almost impossible, because you have always some kind of imperfection from the material or from the node, whatever, that generate a localization, and from this point, you break.
okay.
The breaking, as you said, depends on the difference of the dissipation, which depends on the size, and so you effectively have a size effect. So yes, the answer is yes, and the image that I show you is theoretical one. We just reproduce it numerically, just to show you that we can get it. But the result is fully understood and it's not our result.
I was just wondering, in the case of, let's say, 4-point bending beams, where we don't have any notch, and we have like a constant moment distribution. And if we want to reproduce the size effect I would assume that we need to input some kind of imperfection to that, or some kind of, I don't know,
Numerically, everything is perfect, but in any case, it will be not perfect because you have some differences in the meshing. The meshing will be not exactly uniform. So even if you have some imperfection due to the meshing on the position of the node, you will introduce an imperfection.
Is this enough already?
Yes.
Okay. This is my question. because
Obviously, if you have a notch, you just start and you.
Yeah.
If you don't have anything to start, easily start the strain localization, you increase the load, and then it blow up. So numerically, it will be very complex to get a solution. But you will end up with the same.
Yeah.
And obviously, the same behavior.
Okay.
Another question. So how these methods actually perform compared to the use of some generalized criteria or the localization, regularization?
I haven't understood the question, sorry.
How these methods actually performs compared to the use of generalized continuum, that the micromorphic approaches are used to utilize the simulation.
There are different kind of method to tackle the strain localization. Each one has its advantage and disadvantages. This is our solution because it is quite easy to be implemented. You don't need any tracking, and it works nicely. You don't have to modify the balance equation as other people does, or you don't have to modify the consider equation as other people does. So, according to our understanding, it is just a problem of what the element is able to catch in terms of strain and stresses. Because at the end of the day, you have a geometry. You have to discretize this geometry through finite element. This finite element has some kind of kinematics. Each one of these has a different kinematics. If you have a finite element which includes more degrees of freedom, it allows you to do more things. It is more powerful, more option. In particular, in principle, if you have this pressure control, you can control the pressure instabilities. If you have strains, you can contribute to the accuracy of the solution in terms of strain and stresses, and particularly to catch the direction of the cracks. I can understand that there are other possibilities in the market. My advertising is just, I don't want to sell you the mixed formulation. I want to sell you the idea that if you go a step further to the elastic limits, take care. Because the solution, as I show you, in both mode 1 and mode 2, suffer of isochoric problems or suffer of mesh dependency. How to solve this? Well, the world is full of people with different ideas, so this is just our idea.
Okay.
Thank you very much.
Okay.